Okay, sorry. So thank you for the introduction. I'm Arata Amemiya from RIKEN. I'll be talking about 1,000 member 30-second update real-time precipitation forecast experiment using the supercomputer Fugaku. So the previous slide, previous presentation by Yashiro-san also focused on the large-scale computation using Fugaku, but this study focuses on the simulations with more smaller scale and a short period. So the computational speed is the highest priority. So yeah, my talk will focus on it. Okay, so the introduction of supercomputer Fugaku, maybe I can skip some part of this slide as Yashiro-san did a comprehensive introduction. So the full operation of the Fugaku started in March 2021 after about 1 year of early partial use for prioritized projects, including Yashiro-san's Grand Challenge and some other studies related to COVID-19 researches. So now it's in a full operation. And the main aim of Fugaku is building a step towards society 5.0 by synchronizing simulation, AI, and by big data. So the big data simulation is also one of the most important study subjects using Fugaku. So to demonstrate the applicability of big data simulation in real-world problems, we performed real-time precipitation forecast experiments last 2 years. In our experiments, 30 minutes precipitation forecasts in Tokyo and surrounding areas were calculated and disseminated every 30 seconds. And unlike the most operational nowcasting schemes, we used data simulation and numerical weather prediction model to provide forecasts. And our system includes not only real-time calculation, but also the real-time transfer of observation and forecast data. So in the summer of 2020s, we performed the experiment using 50 ensemble members as we are not able to use Fugaku. But last summer, for the period of Tokyo Olympic and Paralympic Games, we attempted to do it a similar experiment, but with much larger size using Fugaku. So we used a phase array weather radar power in our experiment. The power provides observation in much higher spatial and temporal resolution, such as every 30 seconds. So with this very high temporal resolution, we can capture the rapid evolution of three-dimensional distribution of the rain intensity in developing convective clouds. There are a couple of powers in Japan, and among them, we used the multi-parameter version of power, MV power, located in Saitama Prefecture, north of Tokyo. So, so far, we have developed the data simulation and the numerical weather prediction system called Scale LETKF, combining the LETKF with the regional numerical weather prediction model, Scale RM. And in earlier studies, we demonstrated that the Scale LETKF is capable of performing data simulation of power observation within 30 seconds that is necessary for real-time calculation. And in the summer of 2020, we actually did the real-time forecast using actual observation data. Then last summer, the challenge was to expand it to much larger scale ensemble size using Fugaku. Okay, this is the workflow of the real-time forecast. The system composed of the outer and inner domains. In the outer domain, with 1.5 kilometer grid spacing, 9 hours ensemble forecast is performed with 1,000 members, driven by JMA mesoscale model data with some perturbation. And then the forecasts are downscaled to 500 meters to provide initial and boundary conditions for the inner domain. And in the inner domain, data assimilation cycle is performed as it received the observation data every 30 seconds. Simultaneously, the extended forecasts are performed with 10 member ensembles in the same job. So the inner domain data assimilation and forecasts are performed in one big job using 8,888 nodes. Okay, so this slide shows the data stream. The observation data from Saitama MP Power is transferred directly to the job running on the Fugaku. This is enabled by the special program called JIT-DT, dedicated to this purpose. And this data transfer is done every 30 seconds, and the average time for it is about 3 seconds. We also need JMA model data, and this is updated every 3 hours. The output files include forecast image files and netCDF files for visualizations, and they are generated and transferred every 30 seconds as well. So there are several technical difficulties in performing 30 seconds data assimilation cycle with this large number of ensembles. First, LETKF takes longer time as the ensemble size increases because mainly due to the eigenvalue decomposition part. So when the ensemble size is 1,000, this is a big issue. So in our study, we also used the single precision and the efficient eigenvalue solver called KBD. So panels on the right shows the comparison of the elapsed time for a single DA cycle. So so using this new solver with single precision improved the efficiency very much. Also, we conducted experiments to determine the necessary number of nodes that for real-time calculation. So most components in scale LETKF can be made faster when the number of nodes is increased up to 8 per member. This corresponds to 32 subdomains for one member. So that's how we made the 30 seconds update possible. Okay, we also made a careful treatment in the data access control. So Fugaku has a multi-layer storage system that is effective for jobs with a large number of nodes. The standard HDD storage is considered second layer, and there is a first layer temporary storage assigned to each job. In the beginning and in the end of the job, we need to copy the data between the second layer and first layer temporary storage, as we call it stage in and stage out processes. And using first layer storage in this way, we can avoid the possible trouble of too many access from many different nodes concentrating on one same address in the storage. One exception is the output files that needs to be generated every 30 seconds and immediately transferred to external servers. So this shows the schedule of the node usage in a day during the experimental period. The biggest job for the inner domain runs continuously for 24 hours. Whereas the job for the inner domain, outer domain forecast and downscaling runs every 3 hours. So in total, we used about 11,000 nodes. So, so let's see some of the results of our experiment. Well, I hope you can see the image moving. During the experiment, the forecasts are disseminated and displayed on our website and also smartphone applications, and they are updated every 30 seconds. So on the right, experimental three-dimensional visualization of both deterministic and probabilistic forecasts are shown in this smartphone app. And this is the example of the forecasts shown on our web page. In the case of the most significant rain event during the period. So the image above shows analysis at 15:30 JST on 30th of July. You can see the area of heavy rain over the central Tokyo. And also there's a fine scale structure showing the couple of convective cells emerging in the western part of the rain area. And the bottom images are 30 minutes forecast at the same valid time. The left one is the single forecast, and the right one shows the area where there is significant probability of the rain exceeding 30 millimeter per hour. So in this event, the rain distribution was at least partly reproduced, but at the same time, there are features that is not accurately predicted. So there are still a lot of things to investigate to improve the forecast. Well, the experiment was successfully done from the technical point of view, as we calculated and disseminated the 30 minutes forecast for the most part of the period. So this shows a summary of the forecast lead time over the first part of the period from July 21 to August 8. The gray area corresponds to the time when the forecast was not available for the technical troubles. But except this period, forecast lead time was usually between about 27 and 28 minutes. So this means we successfully provided the 30 minutes forecast with only 2 or 3 minutes delay. Okay, so this is a summary of my talk. So my talk was about the real-time precipitation forecast experiment with 1,000 members and updated every 30 seconds. So the important factors were the single precision and advanced linear algebra algorithm and the MPI parallelization. With these efforts, we successfully provided 30 minutes forecast in a real-time manner continuously for the most of the experimental periods. So I hope we can improve our scale LTCAP system based on the experience of this real-time experiment. So lastly, I would like to share the video clip of our project recently made. So this is originally made for AGU TV, but now it's also available online on YouTube. So yeah, we appreciate it if you are interested and visit our video. So thank you for your attention.
Thank you very much, Arata, for this nice presentation. And there are already 3 questions in the OPAD, and I will read the first question to you by Lars Nerga. So he asked, is the LTKF actually a good choice at the ensemble size of 1,000 members? The ENKF with perturbed observations is likely faster in this case and should have very low sampling error for such large ensembles. And also with the ENKF, you could apply state space localization. So could you comment on the choice of the LTKF?
Yes, that may be yeah, a good option. Well, we use the LTKF for a data simulation method. Simply because that is the method we have used for long years. So yeah, historical reason. But yeah, that is also a good option to consider. Yeah, to investigate.
Okay, thanks. And Wake Chu is asking, do you really need 1,000 members for this kind of case? is there any cost-effective way to do it also?
Yes, well, if we expected it, well, we expect, well, we can improve the, well, both deterministic and probabilistic forecast is as we increase the number of ensemble size. But, well, yeah, we need further careful investigation. Well, yeah, if we really need that large.
Okay, so did you have a look at like
Yeah.
very rare events or extreme events? Because I would expect that there the ensemble size would matter the most. That you so did you have a careful evaluation of the entire period and check the most extreme events so far, or?
Well, I think the event I showed is the most extreme events during the period.
And could you see any improvement, or like, do you guess that the 1,000-member ensemble was very beneficial in this case?
Well, actually, in this case, the difference is not very significant as well, as we have not fully investigated the optimization of the LETKF scheme in this large ensemble size. So,
Okay.
yeah.
And then the last question by Bruno Ruffin, he's asking, SSDs on Fugaku are accessible to all nodes or only to subgroups of nodes? So if you are in the second case, how do you ensure the migration of data when the propagation code runs on nodes that do not have access to the SSDs? So
yes, well, actually, Fuga subs both of them. So, yeah, well, okay. So, yeah, well, Fuga subs both, well, local temporary space and, well, shared temporary space. So, and the shared temporary space can be accessed from all nodes in assigned job. So, yeah, so, well, some files that needs to be shared by all members are placed there. Well, did I answer to the
I
question?
think you answered the question, yes. That makes sense. Okay, thank you very much, Arata. And
thank you very much.
Stop sharing your screen, and I will hand over to Ting Chiu from RIKEN. She will chair the second half of the event.